solids. And here are today's objectives. And first, we want to learn HCP crystallographic directions. We want to learn crystallographic planes. And then we will learn linear and planar densities. And finally, we will learn this X-ray diffraction, which is a very, very important one to identify the crystal structures. First, we talk about linear density. So as the name suggests, linear density means that the density along some direction, I'm telling you, linear direction, linear density of atoms. And so it is denoted using LD, and which equals the ratio of number of atoms to the unit length of direction vector. So here, this crystal structure, we can see clearly this crystal structure for in this direction, for this red arrow, in this direction, or we know that this direction and this direction is 110 because x, y, z, it is in the plane that is parallel to the xy, oxy plane. So that's the reason this guy, the third direction, third parameter equals 0. But because this is also a diagonal in the plane, that is, we have 110 here. So also the length, the side length of this is cube equals a. We can see based on this definition, how can we calculate this linear density? First, we calculate number of atoms along this direction, and within, I'm talking about the number of atoms within this cube, right? Because it is periodic, repetitive pattern, and outside the cube, there is another, the cube, cube. So we have this 110 here. For along this direction, we say this one is the origin from here and to this corner, this diagonal, and how many atoms we have. We know that here is one atom, right? So this is one atom in the middle. That means this along this line, we pass. This is one whole atom, and in the middle here is one. This is the 1/2. So here is the 1/2. I'm talking about linear density. I'm not talking about volume. Okay, so this is very, very important. I only think about everything within this plane that is parallel to this x or y, and also I along this direction. I don't think about any other direction. So for here we have, this is one atom. So this is the half atom. This is a half atom. Half 1 equals 1, and then plus another one, and we will get the 2, the number 2 here, to stand for the number of atoms. Any questions regarding this? So this is very, very important. We are talking about linear density. We are not talking about the volume density. This is very, very important. We only focus on the atoms in this direction on this plane. All right? Otherwise, you will be confused. Because some students might think that in our last lecture, Dr. Ma just told us that, so this is the 1/8 corner, that is 1/8 corner. I'm talking about that for that is a volume. But here, I'm talking about this, the plane, on this plane. So then, without any questions about this is a numerator, about this denominator, we just based on the definition, unit length of direction vector, unit length of this direction vector. So first of all, you should know that this is a vector. So we know that here is a, then so the length is square root 2 multiplied by a, right? Because it is a cube, and this square. For the square, we have 490-degree corners, and so as a result, the diagonal line equals square root 2 multiplied by the length of the side. So this is based upon Pythagorean theorem. Any questions so far? So one thing I want to emphasize is that this linear density, this guy's unit is nanometer minus 1. So this is, that means 3.5 per nanometer. This is kind of strange, okay? But based on understanding, you should know that. You can see the unit of this numerator is number. Number, that means this one does not have the unit, just the number. And unit length is a meter or nanometer, centimeter, nanometer. We use seldomly. We use the centimeter here. We use meter, millimeter, this micron, meter, and the nanometer. So this kind of 10 minus 3. So this is the level of this measurement for length. Any questions? No question? We talk about the HCP crystallographic directions. So here is a crystallographic crystal structure. Okay, so the algorithm for this direction we have, you can see we can have, this is a plane, so we have, this is a kind of volume, you can see this is 3D, vector repositioned if necessary to pass through origin. So we always we want to, for convenience, that is definitely is artificially established the XYZ coordinate, but for convenience we just use vector reposition is repositioned to pass through origin, right? So this is give us a lot of convenience. And rid of projections in terms of unit cell directions, and A1, A2, A3, that is A1 along A2 and A3, or and this is a C. And these are adjusted to smallest integer values, and then enclosed in square brackets and no commas. Be careful, and this is a square brackets. For example, and for this direction, this is the center, also is the origin of our XYZ coordinate system. So here, so this is in this direction, and I'm going to show you how can we get 1, 1, 2, 0. And here, if we just look at this is the 2D, this is a plane, and we have this is hexagon here, and so this is the center, and so here is this is a vector here, and so this is A1, so this is A2, and we have this A3 here, right? So A1, A2, A3. You can see very clearly. So this is A minus 3 because it is in the opposite direction. Because dashed red line indicates projection onto A1 and A2 and axis, and this is based on bit of projections in terms of unit cell. And here and here we do the projection, and then because we know this is 60 degree, so this is 60 degree, and so this is red angle, and based on the trigonometry, and we know so this is the length of this is the side is A2 divided by 2 because this is 30 degree, and same thing here. The projection of this vector on this A1 direction, that means here, and this guy's length equals A1 divided by 2 also, because here is a 30 degree. So we have 1/2 A1, 1/2 A2 minus A3 and 0. Why is it 0? Because in z direction we have 0. Because I'm just talking about this vector which is located on this bottom surface, bottom plane. But then hexagonal crystal, for hexagon crystals, these are 4-parameter Miller Brevis lattice coordinates are related to the direction indices, and that is we call u prime, v prime, and w prime as follows. Okay, so I'm going to show you guys u prime, v prime, and w prime, and we use this one and we calculate the uvtw based on these equations, and you can see here. So this u1, right? So here, as long as after you get u prime, v prime, w prime, and you can use these 4 equations, get uvtw respectively, and based on this equation. And then we talk about crystallographic plane here. So here is we can see this is a cube, and this is a cube. We have 2 cubes, and so here, so this is 3 green planes. They are equivalent, and all of these 3 green planes, they have 001 planes. They are designated as 001 planes. And same thing for here. Here is 1 cube, another cube, another cube, 3 different neighboring cubes. They are arranged one by one, because we know that. So this is for metals and for the crystal, and we have for crystalline material, we have repetitive pattern for these units. So we can see this is the lighter green. So these 3 planes, they have the same direction. Okay, if we just look at each of these cells, we found that they have the same direction, and as a result, these 3 guys, they are designated the same as 110. Do you understand? The same thing, and for this one, and for this is a rectangular shape, and here is a triangle. For these 3 triangle, and they also parallel to each other because they are in 3 closely arranged. This is the cubes. So these 3 directions, these 3 planes, they are parallel to each other. So they are designated using the same number, 110. And then we talk about crystallographic the plane, called Miller indices. Miller indices reciprocals of 3 axial intercepts for plane, and cleared of fractions and common multiples. All parallel planes have same Miller indices. I want you guys to know this is called Miller indices. Miller is a scientist. These indices are named after him, Miller. Algorithm, there are several steps. First, read off intercepts of plane with axes in terms of ABC, right? ABC. And second, take reciprocals of these intercepts. Third step, reduce to the smallest integer values. Lastly, enclose in parentheses, no comma, HKL. So this is the plane, right? So you need to know that this is the plane. And for the direction, we told that we use a square bracket, but here we use a parentheses. So be very, very careful. So here is give you guys an example. So this is a cube, XYZ coordinate system, A we call A stands for X, B stands for Y, C stands for Z, and in this plane, this blue plane, intercept these three axes, X, Y, Z, in one, right? One, infinity. Why this infinity? Because this plane is parallel to the z-axis. That's the reason the intercept of this plane with this z-axis is infinity. That means these two guys will never ever intercept with each other. And then second step is take the reciprocals of these three intercepts. One's intercepts equals 1 itself, 1 equals 1 itself, infinity, 1 over infinity equals 0. Do you guys agree? Okay. And the third step, reduction. 110 is 110, and reduction, and still 110. And so, as a result, meter indices for this plane is called 110. Any questions so far? Okay, no question? And so second example. And second example, the same XYZ coordinate system, but now we use red square, red plane. This you can see this is red plane. And this red plane intercepts these three axes at 1/2 for A or X, because this guy is parallel to Y, parallel to Z. So as a result, these two intercepts equal infinity. And then for this second step, we take the reciprocals of these three intercepts, and we will get 1 over 1/2, 1 over infinity, 1 over infinity, and then we know that 1 over 1/2 equals 2, 1 over infinity is 0, and this also is 0. And so reduction, we have 2, 0, 0. So as a result, its meter indices equals 1, 0, 0. Actually, it's 1, 0, 1, 0, 0. Because the 2, 0, 0, we can just divide each of these numbers by 2. We still have 1, 0, 0. This makes sense. But this one, if you write this way, it is fine, but it's not concise. We use this one instead. Third example. So this third example is an oblique plane. And this guy intercepts the three axes at 1/2 here. You can see 1/2 here. B for 1, C 3/4 from the origin, from here to here, and 3/4 of C. Reciprocal 2, 1, 3 over 4. Now 3 over 4 is a fractional. And how can we do that? We do the reduction. How to do that? We multiply these three numbers by 3, and then so this one, this fractional number will become an integer. So this is 3, and this is 6. And the result, this guy's meter indices equals 6, 3, 4. So family of planes, keep in mind, family of planes, we use parentheses. Family of directions, we use, what we use? We use, this is a square bracket. And remember this one, okay? This, for example, and this is a bracket. We call this a bracket. So this one equals 100. So I'm sorry. So this is in meter indices. So this is a bracket. So this bracket equals 100, 010, 001, and this 1 bar 00, 01, 01 bar. I'm sorry, no, this is a bar on the 1. This is 001 bar. So this is a family. And then we talk about crystallographic planes. A family of planes contains all planes that are crystallographically equivalent. And that means having the same uh, atomic the packing. So, for example, family of planes HKL. So for this one, okay, for this one, you can see reduce the sphere FCC unit cell with the 110 plane. So this one. B. Atomic packing of FCC 110 plane. Corresponding atom positions from A are indicated. So here. So here for this one, so this reduces sphere BCC unit cell with 110 plane. So you can see here atomic packing of a BCC plane corresponding atom positions from A are indicated. Do you understand? And if you have questions, ask me now. If we do not have questions, we move on to the next step. And then we give you an example for crystallographic planes for HCP. Now, this guy has 4 parameters. Intercepts using the same procedure. Intercepts, for example, for this red plane, intercepts here, and on A1, A2, A3, and also Z, these are 4 axes, and we do the projection. Okay, we do the projection. We will have intercept. I'm sorry, the intercept. And this intercept, A1 is 1. 1, infinity, because why this guy is infinity and with this A2? Because this plane is parallel to A2. And A3, okay, this is A3 here, and we just extend this one in opposite direction. So -1. C, it intercepts is a Z axis. The axis here. So reciprocals, and then with reduction have 1 0 -1 1. Middle braces indices, we just minus number, we just put a bar on this is the absolute number. And then we talk about this virtual material science and engineering. So here, VMSE is a tool to visualize material science topic, such as crystallographic, graphy, and polymer structure in 3 dimensions. So this is very, very useful, the tool. I think if you buy this textbook from the bookstore, I think you will get a disc, or maybe now it's not a disc anymore. Maybe you can get some separate files that contains this tool. So VMSE, metallic crystal structure and this crystallographic module. VMSE allows you to view crystal structures, directions, planes, etc., and manipulate them in 3 directions. So you can just take a look, and I think it will be very, very intuitive, and also will be very, very thought provoking and a lot of fun when you learn this crystal structure using this VMSE. And what's here? Unit cells for metals. So this is the VMSE allows you to view the unit cells and manipulate them in 3 dimensions. And below example of actual VMSE screenshots. And crystallographic plane exercise you can do. You can have this exercise here. You just take a look. And then we talk about atomic packing factor, BCC. And then planar density of 100 iron. And so here's a planar density, and this is a solution. This is at T less than 12 degrees C iron has a BCC structure. I told you guys we have alpha iron, beta iron, and gamma iron at a different temperature. And so here is a BCC here. So this is a 2D repeat unit. And how to calculate this planar density? Planar density equals on this plane and how many right? So on this plane repeat unit and how many items? These items we have one, right? So because this is a one corner, four corners, quarters, we have this one here. And so here is a plane a square. So this is a square. This is a square here. And what is a? How to calculate this a here? So this is a side, okay? It's the side of this square. And this guy equals 4 square root 3 divided by 3 multiplied by r. And so we just plug in and we can have this value. So this r is the radius of this item. So you can see this planar density and this gas unit equals atoms per meter square. It's a very, very huge number. You can see huge number. And you can imagine in a square meter area, how many atoms we can have. I would say so small, right? This is understandable. The huge number is understandable. The planar density of iron. So this is a plane, another plane. So in 111 plane, so one atom in plane you need a surface cell, right? One area, one atom in plane divided unit cell. So this is the atoms in plane. So these are atoms above plane and these atoms below plane. So this H equals square root 3 over 2 multiplied by A. Right? So this is a 2D repeat unit. So based on this one area, we can calculate square root A multiplied by A multiplied by H, A square, right? And A equals this part, and then finally the area can be obtained using this equation. So, and then we can use this definition of planar density and to calculate its number. And this is also very, very huge because the unit is kind of weird. Atoms per meter square. This VSME planar atomic arrangements allows you to view planar arrangements and rotate them in 3D in 3 dimensions. Here I cannot rotate, but if you have access to the VSME, the tool, and you can just rotate it in any direction. So this is a BCC 110 plane. And then we talk about single crystals and polycrystalline materials. Single crystal and polycrystal, as the name suggests, this is a single crystal, but this is a polycrystal. Single crystal for crystalline solid, when the periodic and repeated arrangement of atoms is perfect or extended throughout the entirety of the specimen without interruption. So we call this one as a single crystal. However, the polycrystal composed of a collection of many small the crystals or grains. So this is the neighboring crystals or grains. They have different directions, different spatial arrangements. So this is the polycrystalline. And then we talk about X-ray diffraction. X-ray, which is very important technique that we um, you need to learn. So here, this electromagnetic spectrum, this frequency, hertz, and these long radio waves. So this is FM, TV, infrared, ultraviolet. So here, from here to here, this is a visible light. So here is a gamma rays, these microwaves, AM, these are shorter video waves. So here is X-rays here. So here, this is a frequency, and so this is the wavelength, right? So this is a frequency and wavelength. So diffraction gratings must have spacings comparable to the wavelength of diffracted radiation, the diffracted radiation. So cannot resolve spacings that is less than this lambda. This lambda is the wavelength. The spacing is the distance between the parallel planes of atoms. That's the reason we talk about the spacing first, then we talk about X-ray diffraction. So this is X-ray to determine the crystal structure. So here is the incoming X-rays here, X-ray. Diffract from crystal plane. So this is incoming X-ray. So this is the first one, and second one, and then coming back, outgoing X-ray. So this is a detector. So this actual distance traveled by this wave 2, this wave 2, this wave 2, this wave 1, and this wave 2. So you can see spacing between planes. Reflections must be in phase for detectable signals. Reflections. So measurement of crystal angle, this is theta here, allows computation of planar spacing. Planar spacing D. X-ray intensity from this is a detector. So this is theta C here, right? So this is theta C. Once you get this is a theta C here, and you can use this equation to determine the D. This is called Bragg's law. So X-ray diffraction pattern for different the planes, for different planes, for polycrystalline alpha L BCC. For this 110, we have this intensity, right? So this is a 200, 200. This is a 211. This is they have different this intensity. So this is stands for so this plane 110 plane. So this one is a 200. So this plane is parallel to YZ and only perpendicular intercept with this X axis. And 211 is this is the oblique plane 211. So summary, atoms may assemble into crystalline or amorphous structure. So common metallic crystal structures are SC, and I forgot to write SC here, SC, FCC, BCC, and HCP. Coordination number and atomic packing factor are the same for both FCC and HCP crystal structures. And be very keep in mind these special facts. We can predict the density of material provided that we know the atomic weight, atomic radius, and this crystal geometry. For example, FCC, BCC, or HCP. Crystallographic points, directions, and planes are specified in terms of indexing schemes. So crystallographic directions and planes are related to atomic linear densities and planar densities. So materials can be single crystals or polycrystalline. Material properties generally vary with single crystal orientation, and that is they are anisotropic. Anisotropic means that we have different mechanical properties or different other properties in different directions, but are generally non-directional, and they are isotropic in polycrystalline with randomly oriented grains. So be very, very careful about this. So some materials can have more than one crystal structure, and I told you guys this is referred to as polymorphism or allotropy. The examples is the iron, we have alpha iron, beta iron, gamma iron, also alpha titanium, beta titanium, and for this carbon we have this is a diamond, we have graphite, and I'm also going to talk about this fullerene, which is a soccer ball made of 60 carbon atoms. And also the fourth form of the carbon is this is the carbon nanotubes. So this is you need to know that these are basic facts. And then we talk about extreme diffraction that can be used for crystal structure and interplanar the spacing determination.